having me. It is a great pleasure. And what shall I say? The topic for this lecture was not set, so I needed to find a topic and I needed to find reasons and details to talk about. And the first thing is that please feel free to discuss. So if you have any questions, raise your hand, stand up, or just take part in the discussion. Because what we do is mainly about discussion, and so we should have that here too. I think we just start. I'm a structural engineer. I want to clarify this because what Mario said is this interaction with architects and engineers, and there's always a thing going on. I know a lot about it. And so I want to try to define my role or explain that by doing or explaining what I do in the projects or what we do. And this is a little bit the way I got the ideas for the title. The first thing was I'm an engineer, nothing else, and stick to that. The next thing is I'm not an architect. And it's also a bold statement because usually there's always somebody saying, aren't you an architect? What are you doing here? Aren't you an architect? And I'm not, and I have no intentions to be one. What I do is I design load-bearing structures. This is basically the backbone of any building. Holds it up, gives it its shape. This is what I do. But that is also a little bit wrong because I don't do it myself. I do it in a collaboration, I do it in a group, I do it together with other people. It is not I who build. That was the last adjustment. It is we that build. And the we build discussion is not my office builds or my people builds or the engineers build. It is we all together, which is a little bit, is maybe very easy to understand for architects. It's not so easy to understand for engineers and engineering students. I hope there are some here today because that would give me some backup. Otherwise, I feel a little bit alone. So if there are, please, interesting questions. So we all together build, and this is what I'm going to show is a little bit in this context that we contribute. You need to understand what we can do, what we can't do, and how we interact. And this is a little bit what I try to explain in examples. I show projects in a chronological somehow order about the projects of the last 5 years. And a little bit about my history. I'm German, I have a German engineering degree. I came to Norway by accident. I stayed by accident, and it has been exciting ever since. So I intend to stay. And I've been studying at the School of Engineering in Stuttgart, and they had a very famous professor, Professor Schleich, and he was one of the pushing always the limits, and he was always about social responsibility as an engineer. That is something that is, usually engineers, they do their stuff, they focus on that, and that's what they like, but he had always this attitude to save the world, and it was renewable energy long before it was an interesting topic. And further on, I started working at Norconsult, one of the big consultancies here in Norway. And after 9 years and a long discussion with myself, I started my first office. And I had a period of this at the School of Architecture where I was lecturing and working with the students. And that was a lot fun because you had this interaction, you learned to discuss, and they had all these weird ideas, and which you could shape, but on the other side, make a nice project out of. And so that was fun. And now I'm talking about the period after, from 2007. The first real thing was the Oslo Triennale in 2007. It was the culture of risk. It was an architectural triennale where they wanted to investigate risk-taking in architectural projects, and they wanted to compare that to engineering projects. So we had a top 10 engineering projects in Norway, just to understand what kind of risks they take in those projects compared to what they take in architecture. And it is quite fantastic. Alta is the hydropower Norway is self-sufficient on power, electrical power, because of hydropower. And they are, you can think what you want, but they are amazing engineering structures. Same thing is with these high wind windmills offshore. It is amazing what they achieve. They had the longest road tunnel for a long time. They have these mobile rocket shooting platforms. Amazing things, didn't work out economically, but amazing. Snøhvit is one huge project. I worked personally on this one, did the steel design for all the stuff on the barge. Fantastic. We should always mention the Troll A. Tallest, it was up to, I think, until a few years, it was the tallest structure built on Earth, except for radio towers. Excellent concrete quality, and that in the 90s, perfect. This expo design is very innovative, so engineering is strong in Norway. Architecture, this is just taken from Wikipedia, so it's a very, it describes architecture is both the process and product of planning, design, and construction. Architecture is the whole thing. And I like this phrase because it fits very nicely to this Webuild attitude. We all work together to plan, to design, and construct to the finished building. Holmenkollen was a trauma for me that has been talked over many times, and I always need to go a little bit through it just to understand it better. For me, it's a healing process somehow. Sorry about the formatting. We had a technical Mac to Windows issue. So you know, don't do that. And it started in 2007. I was asked to join an architect, which afterwards didn't want to do the competition. But I got interested, and I really wanted to do it. So I started investigating it, and I started investigating everything around ski jumps for that structure. Because it was so, it was one of the structures where you know, or one of the projects where you know there would be a structure, there would be engineering content that would be very interesting to work with. And then this is already the result. I want to skip all the steps in between. But what I want to show you is what impact does engineering do? It was obviously clear from that picture, which I took to study the effect of what would it be if it is a cantilever. I mean, that's so obvious with this structure. So I put the tree in front of the concrete column to get rid of it and get an impression on what the old structure looked like as a pure cantilever. On the other side, I was never interested in building a cantilever because cantilevers, they need massive structures down here to take the cantilever moment from the cantilever. And so I was not interested in that. And what I proposed was a bridge, a beam, with a cantilever. And by doing that, you don't need to put the cantilever moment into the rock. The consequences are that you are able to have an open plaza. You see that these people standing here, they have an open space. Could be amazing to walk from here to there. Unfortunately, the finished project did not, it wasn't possible to build of different reasons, mainly due to politics. But the original idea was to have a support here and a support here. And it started out that the architect wanted to build this cantilever, and I said, yeah, well, then let's move all the program in there, up here, and make a single support for this. It changes the architecture. It also changed the way you saw at the top, because during the competition phase, I did a lot of investigations on structures for sure, but I was also the one who was in Oslo, who knew what was working with the old structure. And and I was very much up into the platform. There needs to be a viewing platform or something, and that got incorporated. You see the problem here. This is, for illustration, the second place. They have this huge structure down here, which they use for the cantilever moment. Completely different setup. Rest looks pretty similar. It's a concrete structure, but that was also an intention here to keep it simple, to have a structure that can easily be built. Therefore, it's steel. That is not too expensive, that can be done in the time frame. And so concrete wasn't really what we wanted to do. And you can see this structure. It could also have worked in concrete. It would have just changed the materials. The concept would have been the same. But the steel design, that was done already with constructability and trafficking in mind. You see also other concepts. They had this cantilever and the huge structure down here you need to have a compression foundation, and here tension anchors, but everything closed up for the architecture. This one didn't, but it was very thin anyway. We wouldn't know how to build this. But they also had the opening, but the cantilever moment, that was taken in this part here. The viewing platform, it came out of the rhythm of the truss system. I had these vertical trusses, and I had the diagonals in tension. And the idea was to make the tension diagonals disappear, so you would not see a truss system. And I did that by following the concept of translation of this upper line down to the lower one. So you have these short compression cords, and you have the long tension cords, which could be thin and could be any shape because they are not buckling, tension and compression. And that worked quite nicely. And since I understood the geometry from the competition phase, I don't want to go into details. We made the geometry. It's a 2D drawing that defines the lines of the whole structure. And the concept was to use just this drawing according to the wind profile, which was given by the wind engineer. And the levels here, they were given by the architect. And that was about it. And so I made this shape. And from that on, it went further into the 3D geometry of the whole system, which then was built like that. And you need to understand the structural concept for that, and you need to understand the geometry, and geometry is changing at all places. So that was the way I did it, and then put it into a structural analysis software, and then design it, and then take all the member sizes back, and then the member sizes go for interdisciplinary checking, and then you build it. But I want to skip these things a little bit. This is construction. It is very important to think construction, especially with these projects, engineering. Huge engineering content, always problems with construction. But the concept that we proposed, that was really workable. There were several entrepreneurs looking at the structure, but the one chosen, he used exactly the system that we proposed, and he extended it a little bit with a smart mounting procedure. He invested into this huge crane, which could take modules and lift them in, and he had a special mounting. It was these mounting techniques which were very effective and necessary to make it work. So that worked quite nicely. This detail here maybe shows a little bit of the complexity that you experience in these structures, especially when things get non-linear, out of the square. It is real fun. It takes time, and it always gets underestimated. So take your time. It really requires knowledge about geometry. We have all the tools for it. There's no problems with the tools. But it is hard work in detail, despite how well our tools are developed. We used Tekla, and it worked. But to do the engineering of such a detail, designing the welds and finding the structural systems, that alone requires looking into the 3D model. Otherwise, it would not have been possible. And then drawing it up is the next thing. This also shows one of these diagonals. And the diagonal is attached to the vertical. And the diagonal is, you can see it here, it's twisted 90 degrees. So it does not stand vertical. It would be easier to have it vertical like this sheet, not horizontal. And I'll show you what the effect is. This is the effect. You don't see them anymore. You only see the verticals. And in this way, the truss system disappears. And I like the effect. People take a lot of pictures from this perspective. It also shows a few different things. These plates here, the one that we saw here, this plate, is quite visible. And there were long discussions because they did not trust me on these ones in tension only and flipped horizontal. Nobody saw the point. The architects didn't look at these details, and the engineers, they were scared because you don't do that. What you do is you put the diagonal like this, so it would be very visible. But afterwards, I think they started understanding. I got some comments there. The size of this one we try to reduce at best as possible, but it was due to the construction process not possible to reduce it further. And then afterwards, this is just a funny story, just to make you understand how important these details are. These bolts here, they are designed as contact in the hole. The holes always have 1 or 2 millimeters of slip, and they shall be in contact with the steel. But there's a different type of screw, and that works in compression. So you put a lot of tension in the bolt, you press 2 steel plates together, and then it goes in friction. The contractor, he had he had built this as friction connections. The friction connections are very stiff. You see here they didn't have all the paint on. And they're very stiff, and they don't slide until a certain load is applied. So this building was set up, and then suddenly the load came. and these connections started slipping. And the whole thing started moving. I mean, it was a big bang that went through the structure. And the first time this one, the top was up, I was walking up here, the first one up, and then it started doing this shit. It was really, the whole side of the structure was moving because of this 1 millimeter slip. And the noise and the movement was terrible. And on the top, there were two guys from the crane to hook off the structure. They were nervous. They called me afterwards and said, Florian, you know, we always had this discussion about your safety factors, but today we were really happy for them. So there's risk involved in this. And we calculate the risk, we design for it, we check it, we have routines for that and everything. But we as engineers, we are very, there could be something that we haven't seen. There could be something that was not okay. But it is okay. It works. And it has seen severe storms, and it has seen quite some load. And after the bolts settled, nothing happened anymore. That's the reason why the plates are a little bit thicker. And crediting. This is maybe the more serious part that you should be a little bit aware of, is very necessary to motivate innovation and place responsibility for the outcome. If the people behind the building and the structure don't feel that they have the responsibility, or they don't know that they're going to have the responsibility, and if that is not public, there's no motivation to be innovative. Engineers are usually not mentioned, and so why should they do something exceptional? No motivation. The only thing they need to care of is risk and risk minimizing, and that is make it as thick as possible. And if nobody wants to reduce the steel weight for money, we just put it in. Doesn't matter. But you don't need to be innovative, and that is dangerous in this concept that we built, because it doesn't motivate everybody. It's not only the structural engineers, it's all the ventilation and everybody. They need to see it's also their project. The result is still okay, and people like it, I think. What happened in 2010 has a little bit a pre-story. Together with Lundhagen and Atelier Oslo, I won the Dijkman competition for the new library in Oslo. And at that point, it got a little bit too much for me. I thought, now I have been working so hard, and I need to work together with somebody I would like to work together with. I checked out a few companies, and I ended up at Bollinger-Grohmann. The reason was mainly they were very good in building, and they were very good in making concepts. And making concepts and building is related. Only making concepts is half the deal, because you can do whatever you like. The concepts are very patient. First, when you build them, you see where the problems are, and this is where you learn, and this is where you need to revisit your ideas, and you need that experience. So they had that, and amazing projects. They have been around for 30 years. And I'll just quickly show you Matthias Stracke. He's the chief engineer for the new European Central Bank, which was built together with Coop Himmelblau. And he's here in Oslo, and we've become friends, and that is quite fun. They have built the Rolex Learning Center, the EPFL, together with Sana. The Busan, I had this discussion, you know, Holmenkollen cantilever is 70 meters. This one is longer, 10 meters more. And so they beat me there. That's very nice. And the other thing is, this cantilever, they thought, okay, after the competition, we put in a few columns and reduce the risk and everything is, but then the director of that cinema said, no, this was in the competition. We want that. And then the engineers started sweating. But they made it work, and this is a terrible hurricane region and earthquakes and stuff. So it was a challenge, but it is very impressive. And what I want to explain is people can get attached to structures and the architecture behind it, and then they want it, and they want to pay the money for it, which is amazing, actually. This Bernstein Arena is a very geometrical project. They've built the Kunsthaus Graz, and this is wrong. A little bit about Dijkman. This is the one of the competition. No, I think it is an image later. And my company had the first sketch design of that project. And during that sketch design, we extended the structural system which we had found in the competition. This is the structural system. It was basically columns with quite a smart beam system in the top and cantilevers. There was a cantilever which was very interesting. So we developed that further. We had many alternatives. One of them is this one, using columns like trees, and illustrate that and discuss that. Looks like that, but wasn't so popular, so it didn't get chosen. So Mr. Bollinger said, why does a slab need to be flat? And why does it? I mean, this is a slab, but it could also be not flat. And this is maybe the approach that we have. Things don't need to be the way they are. They can be completely different. And we developed together with the architects, which was very interesting. They didn't know what it's going to be. We didn't know what it's going to be. And then we came up with this thing that we didn't know that it could be. And it is, we called it the folded slab. These are cores, the 3 cores. We have columns, and we have light shafts they go through. And then we made this folded slab. And the folded slab is folded concrete, and on top you have an installation floor that makes it flat again. So the slab is still flat, but not really. It is a very tedious, complicated process. You can't just run a program and run over it and that's it. You need to study each detail. You need to see the core. You need to see where are the column positions, where are the light shafts coming in, where is the staircase coming in and up. And so it is very hard work to discuss and arrange all these things and make this complicated geometry work. The result is a slab that looks a little bit like this from the underside. This is the architect's impression, Einar Hagen. And we use this slab, this extreme, to solve the cantilever and hang a terrace underneath. But it is challenging. So I just show you. It looks nice in the pictures, but here you see Matthias' remarks and lots of redoing just to make the things work, the geometry, the structural system, and all user demands. This requires a very tight interaction. And what we usually do is we sit together with the architects, not only in the meetings or in a workshop. We move in, have a desk there, and sit there like in the competition phase all the time, because we need that direct interaction. We need that discussion to find, I mean, the crazy solutions you always find late at night or over beer or somewhere else. It is not usually during working hours. And this is what we find very interesting and gives results. The analysis capabilities we have as structural engineers are not a problem anymore. I mean, we can basically analyze everything that we want to. But it is often a problem that we have enough time and in this project business to thoroughly go through and really take out the full potential. That is, so sometimes you need to allow a little bit for time here. The cantilever problem, this shows a little bit of analysis. This shows the folded slab and its special force distributions. These are actual forces in the slab, and I show you in a bit. This is basically the principle. You use folding of paper. Folding of paper makes a stiff plate, origami in this case. You use the same principle to achieve this slab. And the result is like this. Here you have the folded slab, and here you have difference, and that's, again, the architect's impression. A tiny project, which is also in rough nature. And it is Code who won this competition for Truist Way project, and I think you have seen this project before. And I wasn't involved in the competition and nothing. It was Steinar Bjerke, an engineer in Oslo that I work with. And he asked me, yeah, how could we solve this one? And because he didn't know how to make this cantilevering and what would be the best way to do it. The architect's intention was to make, like you go out for dinner in nature, and you have a blanket, and you fold that blanket up, and it gives these edges. Here you have a little bit of program, and here it's cantilevering 18 meters. So the first thing was, we should do it exactly as the blanket is. It should be in bending, and it should be with concrete, and there should not be beams. It should be like a slab, and it should have constant thickness. And the architects, they came, we need beams, we need maybe a column here, we need this and that. And we said, no, we try to exactly use what you thought of, and then we see how far we get with this. And it is quite, 18 meters of cantilevering is a lot. This room here has 12 meters, I just measured it, and it's 1.5 times this room out over the mountain. Why it works is it's a triangle. So the load becomes less towards the tip. And that makes it possible to distribute all the forces at the root. And the reinforcement drawing is quite simple. This is a sketch, it would be drawn out. But it is quite simple. Here you have this bend, the kink, and it should be built next year, and I'm very excited and looking forward to see this stand. This would be the image that you want to achieve. A column here would not be so nice. And this one is a competition that we did together with Gileadi Helston architects. And we usually sit together with them, and so it was obvious to go. It was an open competition, so everybody could send in, and we wanted to do this competition because of the bridge. There was a phase of lots of bridges that have been discussed, and the main, I also cut a little bit here, the main problem was this bridge would have been close to a big old bridge, and then one bridge competes with the other bridge, and it makes it very difficult to find a solution that covers both and gives the new bridge room and doesn't destroy the old bridge. That was the intention. The structural system that came up, I will also skip a few parts here, how we did that. That is pretty special. I think I show you just the result. This is the result. The intention was to have the mirroring of these arches in the river and make that in a horizontal shape so they talk to each other. That was the idea. But the structural system is more complicated than that. If you look at it in elevation, you see a truss system, you see a column, truss system, column, truss system. In plan, you see two walkways that go up and down towards each other. The structural, I mean, the idea in itself, I started a little bit with an idea, then Franco suddenly, I had this weird support here, but then Franco said, why don't we take the diagonals all the way down? It was just fantastic, that one move. And it worked. So it is more this one. 1 + 1 is not 2, it's 3. And you get these moments where you get this type of collaboration, and then you really find, this is fantastic. This is really working very, very nicely. But you can also have the situation that 1 + 1 is 0.5. Try to avoid that. It's no fun. The structure works in a bit. You have the horizontal plan. The truss system in between is not vertical. And since it is not vertical and inclined, it will generate horizontal forces. These horizontal forces, they are taken by the steel deck in horizontal direction. And the steel decks are also cantilevering off the truss system. I did structural analysis and was surprised how well it worked. And we did not get anything for this competition, but we were so happy that we did this bridge, and I hope someday I find a river to build it upon. But until then, I remember it as a very nice collaboration and a fantastic project. You look at this, I mean, it's amazing. You can bike on one side, you can bike all the way up, and which is fun in itself. There would not be any pedestrian traffic on it, because you could route that on the top. You see a lady here. And they could also explore the view and up and down. So I think I like this concept. Then the killer image, I think it is nice. It works. I think it works quite nicely with the bridge. The Munch project. The way we went into the Dijkman project, that was via the competition. The Munch project, we did not go in via the competition, but the Munch and Dijkman project, they are being designed parallel by the same design teams, but different architects, which is new. Never seen this before, but they wanted to use synergy effects in the projects to design during design and construction. So we made the first part of this sketch project, and then it was a new big contract, and we cooperated with Multiconsult and several others in a group. We called it Kulturplan Bjørvika, and won the engineering contract, the huge engineering contract for these two buildings. And so Matthias was working on the Dijkman, and I moved over to the Munch Museum. The competition I didn't have anything to do with. This is the Munch Museum as you have seen it before. It consists of a concrete block in the back and this translucent circulation part with all the vertical circulation, and there's the podium. What we did, or what is much more interesting, the architects, Herreros, they had a organization chart at the Biennale in Venice this year, and it showed exactly the complexity of how these projects are run. There are many people involved. There's the architect, there's the municipality, there's the Munch Museum, the users, there's the structural engineers and all the, you have many of them, ICT consultants, safety consultants, environmental, landscape, facade, safety, lots of disciplines that are in this part. And they all work together around this problem, this building. And Advancia is the project manager. They are in the middle of it. And you have KIP, which is the representative of the municipality, no half Eindom this is. And they all work together. And what they were not used to working like this. This is more or less a Norwegian model. In the continent, it's more architect is managing everything, and they run the project, and that's it. No discussion. In Norway, it's not like that. But they found out that it is quite a smart way of doing it, because you can interact, because you can discuss, you can develop the project further. You can, if you use it right. And they did that right away. They started making contacts, they started having discussions, and they were very organized in their material. So this project was really fun to work with, and I hope it comes back so I think it is interesting. Heros did a very nice job. And so there was not really much to do, except a few things. The question is not how thin a column can be, but should it be there? This is more, again, the way, how do you look at the problem? Is it only a column? Do you want the column? Or should it be something else? Or is it nice? Which shape shall it have? But I often get this question, okay, you're a good engineer, you say. How thin can you make that column? What shall I answer? It's not an interesting question. It's more like look into the standard and make the calculation, and then you get it back, and that's it. But the question, should this column be there, or what other possibilities do we have, or does it create something more interesting? This is what we had here. So in the competition, their engineer and the architect, they had these concrete chambers without any columns. Open spaces, 18 meter spans, 18 meter, there is 1.5 times this span, without any columns. And I like that too, because I mean, in an exhibition space, you really want to have space. And so I thought, yes, well, that should be possible to solve. Talking to the other engineers, it wasn't so easy to solve, because Hulldecke is the system you use here. It's Hulldecke everywhere, and Hulldecke can also span 18 meters, but not with 5 kilonewtons per square meters, not 500 kilograms per square meter. And so I looked at it and thought, this could be solved differently. First of all, you would use the support around the whole concrete bearing wall. So you don't make it a one-axis system, you make it a two-axis system. Understand that? The load spanning is not in one direction, but in two directions. You can only achieve that with precast concrete slabs, for example. In this case, bubble deck to make it lighter. And then the next thing was, since we have this amazing concrete box, I mean, who is building bunkers like that anymore? No one. So we don't really, usually we have very transparent facades with tiny thin columns, and you can't use that for cantilevering. You can't use that for rigid connections. You can only put vertical loads into that. So I did two things. I used two directions and made a stiff connection to the wall. And that seemed to work. So you make a very simple analysis. I mean, if you really understand how your system is working, you can do this. I think you have seen this equation before at this school. And you can very easily make this analysis. And suddenly you're up in 19 meters. And if that is right, you're usually not that far off. Then you can do a lot of computer analysis and tricksing and detailing, but you are in the right problem magnitude. So this is actually an architectural student who was working as an intern with us, and I wanted to show her this, and she liked it very much, to do this tiny little analysis and find out how far you could span, just to get a feeling for things. And well, we did the real analysis, and it wasn't far off. It was almost the same. You see here the effect of connecting to the wall. you see that this critical area here, that is not over the whole system, and actually it is stiffer than Hülldecke, which was the competitive system. Thinner and stiffer. Thinner, very important due to the regulations, building heights in Oslo, and the discussion with the municipality. So every millimeter was interesting. And if you have 12 slabs, then 100 millimeter on each slab is 1.2 meters, and it was that critical. Very interesting discussion with the engineers about footfall analysis. When you walk, this floor is stiff, but if you have a really long spanning floor, vibrations in the floor become an issue, become a very critical topic. But we could also show that these red dots, too, that was within what is acceptable. 4 was acceptable. So it is, we verified that system and got rid of that column. What I also would like to tell you is when you do things that are extreme, this slab, if it goes wrong, you can't really fix the building. What happens if that slab is built and all these levels, and you walk into the building and suddenly it starts vibrating or cracking or whatever problems you get? What do you do with that risk? And then it's the engineers, they have an insurance for that, and they don't want to use that insurance, and this is how to handle risk. First, you need to show that it works, and then you need to convince the project and the owner, basically, that he will not have problems afterwards. A simple trick is using the argument of the column, because you could actually just reinforce this bit here, so you can put in the column later if that is a problem. You understand the trick? And that is often quite helpful. So when you do extreme things, maybe a mitigation strategy and preparing for a mitigation strategy is good, because usually you don't get a problem. But in the case you get a problem, you have a backup plan. And that makes it easier to build extreme structures. The end result, we help them a lot with this translucent facade, but I think I don't go into details. This is a little bit a fun project. It's one of my favorites. It is a bridge, because we had such a nice experience with that bridge in Slovenia. And we were very sad that the project didn't go further. Then one day, the architect came and said, "Oh, there's a bridge project in the north somewhere." And I looked at it, and it was Totalinteresse. It was a turnkey project. So nothing for architects, engineers, and so on. You need a contractor to build it. And I looked at the project. It was Tromsø is here, in the middle of Norway, up in the mountains where nothing is. And I thought, it would be interesting. And I called a friend of mine. He's a contractor in Austria. And he said, "Yes, that's no problem. You know, we have the Alps here. And we do this all the time. So let's talk about this." And then Franco got very excited, and I was excited anyway. So we thought, let's have a look. Maybe we can get this project. This is the situation. It's a fantastic gorge, 150 meter deep in the in this kind of mountain landscape with a little bit of trees. 150 meter deep, 53 meter span, and no access. You could only walk up there. Maybe the four-wheel drive would not go, these buggies wouldn't go, snowscooter doesn't go, nothing goes up there except walking. And they opened for making an access by road, but it would have been very pricey and it would have destroyed all the nature. So Mr. Bichnow, he said, no, we fly it in with a helicopter, no problem. And we said, yes. I made a few decisions regarding the design, what is possible, what is roughly possible, and how would you build something in this, how would you do the foundations in this landscape? You don't have heavy machinery to do any drilling, you can't do piles and nothing. So I came up with the plan, yes, let's dig them by hand and drill all the anchors, do that all by hand, and which is completely the opposite of what you usually do. You try to use technology as much as possible. So the project turned out to be a bridge optimized like nothing before, and high-tech materials to make it as light as possible. It was aluminium. Bichnow is very good at that, to make it liftable. And you would dig the foundations, and cast foundations at place. This concept was very competitive because we thought a different way than what you usually do. The slab is not always flat. It can be something else if you just open to and think in it. The main reason for the lift-in was that you could not put in a temporary column. Usually if you have a shallow river, you would put in some columns at mid-span and then you set them in place, and that's quite easy. Here you could not put up a crane, you could not put in temporary supports. The only thing that would have been possible is a cable in that you would hang things. But how would you lift up from the nearest road 20 kilometers to this spot here? So the system worked well. But how do we build something that is that light? And it reminded me a lot of university where we had this task: build a bridge over 50 centimeters, make it as light as possible, and it shall carry 1 bar of chocolate. It's a favorite game at engineering universities. And they come up with paper super light, and then they measure, and then they load them until they break. It was the same thing, just real. And we had a lot of ideas. You can see that lots of different schemes that we developed. But in the end, it turned out to be these two, a discussion between those two principles. Franco and the contractor, they were in this line of thought. They liked this a lot. I was in this line of thought, as fluffy, as light as possible. And we found out that this one was difficult because the span was just too long. Just having a beam 50 meters over a canyon, it wasn't just working. This would become too heavy to lift it in. But it would have been a very cool bridge. And so we went into that direction. But that did not work either, because the Sami people in the region, they don't work in squares. They don't have that in their traditions. Everything is round. Everything needs to be round. And that was the first comment we got when we proposed this bridge. The mayor just said, no, we cannot have rectangle. That is Western culture. We need to have something round. Said, okay, what can we do? We can't really make it round. We make it triangle. We couldn't do better because the task was so demanding in terms of engineering and weight reduction that this proved to be the most efficient structure. There's a few smart things in here. We have a huge bracing system in the top for lateral forces. We have, which stabilize the compression columns in the top. We have the bridge beam. The bridge deck is basically helicopter landing platform beams. That's what they use to build them in Europe, in Switzerland. But we changed them a little bit. We welded them together, and we used their tension capabilities to take the tension in the whole bridge. We have ropes, wires that were crisscrossing. The crisscrossing was necessary due to the wind condition, because you had strong winds flowing up and down the valley, and there was a lot of uplift. So that's why we have the wires. This is a little bit of view. There needed to be an aluminium detail so that the sheep don't walk over the bridge, and that worked. What we really wanted to achieve was this bridge without great diagonals and horizontal beams in the top. So you would walk on this. You would walk on this without these beams. You could look up to the sky. You could look down to the waterfall, and it would all be open up. But it was just not possible. The forces were such that it was too risky during operation and during lift-in. But we had so many scenarios, and we were pushing it. We called it topless in several versions, but it ended up with this one. And now I wish I could explain you the thrill of structural analysis. It is, I don't know, these pictures that I show, they are the outside of the onion. It's not the core of it, because I don't know, you need to do the engineering study, you need to be a nerd, and then this is fantastic. And you try to fiddle a little bit here and there, and you optimize a little bit here and there, and then it's a real problem if you don't get this bridge lifted. It needed to be 4,000 kilos, no kilogram more. Otherwise, the helicopter company, they would just not take it. So you make, you try to get rid of everything that is possible. And that's a long process. There's a lot of failing in it. It is trying to understand the structure new. The program can't do it for you. The program is just calculating what you tell it to calculate. But to define what you shall calculate and how you shall do it and how you can stretch all limits, that is your responsibility. And this is maybe something that we engineers are not able to communicate. So I just complain. And I think like Magda, like our architectural intern, she got really interested in this stuff. We have a girl I showed, Natalia, she likes this. She's engineer by education, and she really likes this. But keep that in mind. It is interesting. It is fascinating. This is the structural design model with the lifting cables. And the interesting thing about the lifting cables is, no, you don't use 100 kilos for them. You need to use 20 kilos for them. So you need to call around to everybody to find the lightest ropes. So these ropes are 4 ropes by 80 meters for 20 kilos, just to make the weight limit. That required some radical changes. What also was an issue, since the site access by footpath made it impossible with heavy machinery, this triggered a construction method with almost no environmental impact. You could lift in the bridge, you could lift in all the equipment, you have people walking in there, you leave the construction site with no damage except for the bridge. That was something that the client, the commune, they really liked this. And it worked quite nicely. A little bit about the digging experience. That was in quite cold already, but we needed to do it to find out about the rock quality. We were sleeping in tents up there, and it was fun. Carl Julius, he was the project architect. Myself and Jura, he was doing most of the structural analysis. He was an intern at that point. It worked very nicely. All working together, we built. This is how it works. And same thing again, Franco, Harald Bitschnau in the construction yard. Because the thing that we looked at here is, does it really fit together? So it was test mounted in Austria. It was hung on a big crane just to check that everything worked. And then it was shipped to Norway, because up on the bridge you could not change anything. The low budget forced radical construction and design approaches. I think you have understood that already. But it was only possible to achieve this within this kind of setting, within this kind of Totalentreprise contract, where the contractor, the engineer, and the architect all sit on one table and discuss and find a good solution for all the issues. And only in this setting it could have worked, and that made it so, it was fun to work with. The contractor, he was very eager to save weight. So he was milling these huge plates from 30 millimeters down to 20 millimeters. We needed this thicker part here, but the rest was only dead load. And we had optimized these shapes here so they would not be heavy. So we cut out this piece, that's engineering, and the rest is how you treat metal. They have all the equipment, they have all these milling tools to make these 3D shapes. They just have it, all the possibilities there, and then you can do whatever you like. And they're open-minded. Yes, we want to do this. Oh, we can do it like that. And what do you think about this? And then it's really fun to work. And they're very organized. This is all the construction site equipment. It is one truckload from Austria, including the concrete. It was most efficient to bring the concrete best quality from Austria all the way up. And 2 containers, a toilet, and these special made boxes, they are already prepared for helicopter lift in. They were used to this. And out on this side, if you have forgotten anything, there is no shop, there's nobody to ask to get it. So you really need to be prepared. This is the bridge. And again, they put a lot of effort into loading the bridge, because 1 truck is the cheapest. 2 trucks cost too much money. So he spent a few days rearranging the bridge on the truck before he started driving it up. I mean, otherwise it would most likely not have been possible. The crane here was also used as the crane on the erection side. So you use everything you have to make it work. This is the construction side. You see the container. This is the concrete mixing, all flown in, all within the budget. And the first foundation that was cast here. And we had a cable running across the gorge for as a help crane and for a different thing that is crossing the gorge. And that was the first guy from Bitchnau crossing it, hanging on the rope, and 150 meters deep. It was amazing. I mean, yes, that was an interesting feeling. Natalia, she loved it. She did the drawings for the bridge, and it was one of the big moments. She really loved it. That was the view you had when you were within the gorge. And here they are on the other side, building the foundation there. Everything hand dig. They were super experienced. Did that many times in the Alps, and they didn't ask questions. They just worked and did that in a very nice, efficient, smart way. And on this kind of construction site, you really need the best and experienced people, and they had it, everything organized. That was the bridge as it was mounted, prepared for lift-in. And when I saw it standing there, I got nervous, because when the helicopter comes, the big helicopter, he would land beside there, and there's downwash. There's a lot of wind generated by the helicopter. So I got nervous in the last second and thought this bridge could just tip over the moment the helicopter lands. And then you have gone a far way, but you haven't made it. So we fixed it here a little bit, and it worked quite nicely. But the contractor got also very nervous. What you also can see is the bridge decks, they are taken out. It is only temporary wires that are left to save weight. There's also this end frame here, has not been flown up because it would have been too heavy. The bridge in lift-in configuration was exactly 4,000 kilograms, and it was hanging in the helicopter. He said it was 4,000. I was happy. I could still not believe that he would fly this thing up. And the first moment I saw it like that, that was huge. Very difficult, this helicopter lift in, because the helicopter is not stable, it's not quiet. It just moves around, it bounces around, and the precision of lifting in the bridge is tricky. So we tried it once, and we failed. This part here broke off. It bent off, it hung on the bridge, and we went to plan B, the emergency plan. He went back and set the bridge down, and there we sat with a bridge that was broken and a problem. I've never seen construction workers, the rough people, be so emotionally taken by such a decision. I mean, they had been working round the clock all the time because it's sun up there. And then the very last moment, the bridge got damaged and there was no way out. But again, if you have a nice organization and if you can work together and build things together, I started looking at it, found a quick solution, but we needed a welder from Austria. No problem. We got the welder from I called him, ordered the parts that we needed. He went to the plane, had it in his bag, and 18 hours later, he was in northern Norway starting to weld, which also meant that we need to have welding equipment, and you can't have whatever welding equipment. So Natalia had a huge job calling around, and we found this welding equipment 150 kilometers away. So we got that in the meantime, and the moment he went on the construction site, everything was aligned, prepared for him, and he started welding. He welded through the night. In the morning at 3 o'clock, he was done. And in parallel, we had a different lift-in scenario. The bridge was repaired. It got these manchetten, it got these, and we were ready for lift-in, because if we hadn't done it that day, the helicopter would have disappeared. It would have had another job, and the helicopter is the most expensive thing on this contract. So we only had one more chance, and we changed the system, and the system was basically having lines and dragging the bridge, including the helicopter, out of the sky. With wrenches like this, you have the downwash, you have a helmet, it's crazy noisy, and you need to crank that helicopter out of the air. Only then the bridge was stable enough to be put into its final position. And this guy has only 10 minutes up there, because otherwise he goes out of fuel. It doesn't work in that 10 minutes, he has a problem and needs to go back, because he took out all his equipment and all the fuel to make that lift. So, which he was also kind of, I mean, we got the best pilot in Norway, so, but he was like, oh, this I've never done before, but we will try. And so we cranked it out of the sky, put it into place, and it was a great relief. It was amazing. This is still in lift-in position. You have these wires, these thin wires going up. There came also a cloud in, so the helicopter could not see down anymore. The nerves were just, it was terrible. And I remember that movement when the helicopter went, the bridge was in place, the helicopter went a little bit down, and it did it slowly, just checking, is this okay? And then he went slowly out, and he waited a little bit and checked if everything is okay, dropped the cable very carefully, not on the bridge, to the side, and then he made this brutal move out into the valley. It was super cool. And they were very happy with themselves. Then we have this lift-in of the platform panels, and it was again this wire system that they had built over the bridge, where they lifted them. They were very heavy, I think 250, no, 400 kilograms each. And they were not, you could not carry them. So they were needed to be lifted in by helicopter in the right spot, and then they need to be fiddled in. Worked quite nicely. And the temporary cables could be released. And we had the opening day with bungee jumping. It's one of the most amazing bungee jumpings, they say, worldwide. It competes with New Zealand because it is very deep and it is very narrow. So you get this tunnel feeling, and they love it. I did not test it. The reason being, I would like to at some point, but I trust my design, that is okay. But I was, you know, the harshest treatment of a bridge is usually during opening day, when all the people work on it. So I was so fascinated by having all these people walking over, and they're not concerned. They trust the structure. They think this is okay. And they are scared of the height. And you have these ladies that, you have the railing there, it's not that wide. They're afraid of that side, so they go so far to the other side, and then they look down, and here they're almost over the edge. And it was very interesting. So it was a very good day. And last weekend, I was there up for the first inspection, and the snow came very early. It had never, the last years, it hadn't been so much snow. And you see it is still standing. And this is an impression in this winter. I think the aluminium fits in quite nicely. And it doesn't deform too much, so it's very nice. And this is the bridge in summer. This is not a rendering, it is the build project. Quite spectacular. I'm not sure if I want to show you the next slides. It's a different discussion. It's not a project, it is more something that came out of a discussion. These days, technical complexity, organization, and cost control are driving how we build buildings. And they do that more and more, and the processes become more complex, more working together. However, the value of architecture is very difficult to measure. You can't say it's 2 meters tall and it costs 3.5 million. It is something you need to convince and understand. So some people were making this comparison here, where you see this is Gardermoen with its wave. And if you like that feature, you may not like this more cheaper version, which is the horizontal bridge. This is a way of communicating cost issues. And I find it very convincing, so I want to show you the value of architecture. Same thing you can do for the opera. If you cut away this part, it's not the same as if it had this part. It's very, very convincing that it had to be there. And in cost discussions, if you design a building according to an Excel sheet, you don't understand that. So it's very important to make this. Same thing for the Oslo. I mean, without the towers, they are useless. There's nothing in there. And this was the most horrific. It was a personal insult. But in this case, I called it the value of engineering. So, but it is not the same building anymore. It's not the same structure anymore. And what they all have in common, it's all about the structure. It is the structure that gets changed. It's the price of the structure. It's not necessarily the facade. Here it is less facade. It's more structure of how to pile and so forth. So it is quite interesting. And with this, I actually want to close or finish my presentation. And I try to condense it, or what we say in the office is engineering with passion. This is what we try to achieve. And the formatting is horrible, but I think now, if you have questions, please feel free. having me. Let's give